Okay, everyone. Good afternoon. Great to see you here on Halloween. It's my pleasure today to introduce someone who many of you know, our great colleague, our great new colleague, Professor Morgan O'Neill. Morgan got her PhD at MIT in 2015. And then she proceeded to do postdocs at the Weizmann Institute as the Koechlin Prize postdoctoral fellow, and at the University of Chicago as the T.C. Chamberlain postdoc. And then she joined Stanford University around 2019, I think. And we were very lucky when in 2024, she came to join us here in January as an assistant professor on our very own faculty. So I've been thrilled to have her as a colleague. I've learned a lot from her. My graduate students, as they've progressed through their final stages of their PhD, have learned a lot from Morgan. No, she's a great colleague, a great expert in atmospheric science. You'll see her research interests displayed here. They're quite varied. Tropical cyclones, so hurricanes and the storm systems we see in the tropics, their structure, their thermodynamic workings, tornado genesis. These are the severe storms that we find in more the mid-latitudes, the temperate latitudes on Earth. She studied many different weather processes and how these just severe conditions we experience at the surface extend all the way up into the stratosphere and drive the fluid dynamics up there. So very cool stuff. And our interests also extend to the planets and circulation systems on the planets, as we'll hear about. So she's doing all that while still maintaining the Halloween spirit. So you'll get to see that. Morgan, thanks a lot for agreeing to give the colloquium, and let's welcome her.
Thank you. So I've been told that not all of you will immediately recognize that this is the TARDIS from Doctor Who. So for those of you who knew that already, you're nerds. And for those of you who know that now, you're on your way. And I wanted to make sure that the online people can see it. Okay, very good. All right, marvelous. To make a small pregnancy-related joke, I really hope it's roomier than it looks. I was supposed to give this seminar in January, actually, but I'll be a lot larger and crankier in January. And the Halloween date opened up. So we collectively thought it's better for me to speak to you now. All right. So I'm going to review a review in Modern Reviews of Physics. I didn't lead it. I was one of two authors. This work, which I'll focus on, was led by Dr. Marty Singh at Monash University in Australia. We were classmates together. That's a great way to start. Awesome career-spanning collaboration. So maybe the people you're sitting with now, you'll end up writing some papers with, which I tried to do for half of my papers. Strongly recommend. Okay, so thermodynamics of the climate system. We will focus on Earth for a while, and then we will do we'll take a trip to the other planets. But Earth's history over time is actually so dramatic. You can think about paleoclimate as giving us examples of other planets in the universe, because it has had such diverse, dramatic shifts between different climates. Maybe 700 million years ago, and probably that was at least one of the times, Earth was likely covered in thick ice. We call that snowball Earth. Much more recently, maybe, I forget, maybe 70 or 60 million years ago, the mean global temperature of the Earth was much, much warmer. And there were prehistoric crocodiles and palm trees found in Antarctica, for example. And so the Earth's climate has experienced extraordinary, dramatic swings. And these are important contextual clues to what we face when we study climate change. This, to give you a sense of these swings, is a time series where everywhere, can I use, oh, wonderful. Everywhere you see a vertical line here, the scale of time suddenly shifts to a different scale. So we're kind of zooming in on more recent history here. But you can see this PETM, for example, the Paleocene-Eocene thermal maximum, was when we had palm tree-like trees and crocodiles at the poles. And of course, the planet was completely ice-free then. We're in a relatively cold period of the Earth's of the Earth's evolution. Oh, good, I can see it here, and the mouse. And we are now experiencing a very frighteningly fast climate shift, faster than anything we can perceive in the geologic record, in fact. So, you know, some people, when they talk about climate change, they say, oh, well, the Earth has had even more significant climate swings in the past. And, you know, we know. But this current change, it's the speed at which it's happening that is alarming. But I want to focus on thermodynamics, and that was the focus of the review that we wrote together. So this is going to be a really quick breeze through things that you know, but I just want to make sure we all have the same vocabulary for a few of the following concepts. For an isolated system, isolated meaning no mass or energy exchange with the environment, completely insulated from the environment, the total entropy of the system can do one of two things. It can stay the same, in which case it's in equilibrium, or it can increase. And that's due to the second law of thermodynamics. You could have a closed reversible system. And here, when I say closed, I mean that mass cannot be exchanged, but energy can. And in this case, you can actually have a decrease of entropy in your system because you are communicating with the environment. You need not have an increase of entropy necessarily. And you can have reversible losses and sources of entropy due to reversible heating at a given temperature. The Earth is mostly, to as many orders as may matter to you, a closed and irreversible system. So we are an extremely dissipative, highly entropic, irreversible system. We're closed, which means we can exchange energy with our environment, that being space and, of course, the sun. There are a lot of entropy sources that are irreversible. So here we have our change in entropy as a climate system equaling the net import of entropy from the surroundings and the irreversible entropy production on Earth. And in steady state, we can get rid of this time tendency. And we can actually constrain the irreversible entropy production within the climate system, which is basically the fluid envelope of Earth. It's from, you know, maybe the top of the oceans if you think the oceans don't matter much, and for entropy, maybe they don't. Bottom of the oceans if you're an oceanographer, to the top of the atmosphere. This is the climate system. This system evolves and comes to a steady state on timescales that are a lot faster than, for example, the evolution of the lithosphere or our rocky mantle. And so we are going to consider the climate system as just kind of being the atmosphere and the ocean, and then its interaction with the surface layer, which itself we won't consider to change. So certainly on a daily timescale, on a seasonal timescale, you know, we are not in entropy balance. We are not in energy balance. That's why we have seasons. That's why it's cold at night. But if we're taking an average over several years or tens of years, then we can consider ourselves to be in a state of entropy and energy balance. And for us, that doesn't mean that, you know, the entropy coming in equals the entropy coming out. But rather what's happening is the Earth receives very little entropy from space, from the sun primarily. It produces an incredible amount of entropy and then exports all of that back out, such that the total entropy in the system is about constant. And so we can set, if we can ignore this time tendency, we can set the material entropy production of the climate system to the reversible heating rate at some temperature and the cooling rate that we perceive from satellite. So you're all familiar with the Carnot heat engine. It is a reversible, ideal, perfect engine that takes in some Q in energy from a hot reservoir at some high temperature, dumps out a Q out at a colder temperature, and that difference, the entirety of that difference, is exported from the system to produce, you know, to do useful work outside of the system, maybe lift a mass in a gravitational field or something like that. I'm going to argue that we can think of the climate system as a heat engine, but we have to, there are some tricks. We have to do some weird things. An irreversible heat engine, still not a climate system, has some large Q in at a hot temperature, some cold Q out, and it can export less work because it is producing entropy. There are irreversible processes that reduce its ability to do work. And so we can combine the first and second laws to see that there is some Carnot efficiency at which for an ideal engine where there's no production of entropy, we can have all of the exported energy go to useful work for some Carnot efficiency. The climate heat engine is very different. And so we have to calculate things like efficiencies very differently. Q in over these large multi-year, global time averages equals Q out. Therefore, we export nothing. The Earth is not doing work on an external body, okay? But it's doing a lot of work on itself. The oceans are working on themselves and the atmosphere. The atmosphere likewise is working on itself and the oceans. There are large-scale motions. There's a lot of kinetic energy in these systems. And that kinetic energy is eventually dissipated to friction and turned to heat. And so we can consider the climate as a heat engine if we understand that the work is being done on the system itself, because Q in equals Q out. There's nothing to export. But first of all, we have to ask, which climate system are we considering? And there are 3 different ways to do this. And this is a matter of taste and computation. We could consider the planetary system. I want to say one more thing. Determining the climate system is important because we always talk about systems with respect to an environment, right? We are in contact with an environment. What is that environment? Well, part of the problem with this system is it involves radiation. And whenever radiation moves between 2 bodies and is re-released, it produces a bunch of entropy. And scientists have been debating whether that entropy production matters for any of the useful constraints that can tell us about the climate system. So let's first consider the planetary system. That's everything below the top of the atmosphere, or TOA. All of the radiation, so all of the wiggles, all of the matter, so all of the dots, for the atmosphere and the surface. Now that means that we have to keep track of all of the entropy due to radiation. We could instead consider the transfer system, which is a weird intermediate partitioning of the surroundings of space and the Earth system. The transfer system says, let's consider all of the photons that come directly from the sun or go directly out of the atmosphere back to space without meeting any more matter on their way. Let's consider all of those photons as part of the environment. And let's consider all of the radiation that passes between matter to be part of the climate system. So now we've just reduced the amount of entropy that we're producing in the climate system because all of the entropy that's all of the radiation that's directly escaping the atmosphere, and all of that which comes in directly from the sun is part of the environment. Finally, we're going to focus really on the material system. And the material system is the easiest. We're going to assume that entropy production due to radiation doesn't matter. And we're going to assume that all of the heating and all of the cooling due to radiation is a reversible heating or cooling. And so now we only have to think about the heating or cooling of matter and entropy production due to interaction between different types of matter, different arrangements of matter. This is the easiest one. This is the one that people have mostly settled on, but people make arguments about the other systems. And so we can define a Carnot efficiency for the climate system if we go back to this equation, recognize that we can't do any external work, and set eta C, or the Carnot efficiency, to this term that determines the entropy production as a ratio of the total internal heating, which is the same as the total cooling. Q in equals Q out. But there's something else really remarkable and different about this heat engine. There's a negative feedback loop. We absorb energy primarily at the surface and at lower levels from the sun, because most of the atmosphere is pretty transparent to shortwave radiation. And we lose that energy due primarily to convection, drawing buoyant air parcels from the surface aloft back to space at colder temperatures. That sets up a circulation. That circulation is trying to reduce the temperature tendency that allows the climate system to act as a heat engine at all. It's thermally direct, right? We have energy moving down gradient from a hot region to a cooler region. That down gradient process is destroying that gradient, right? And so it is weakening its own ability to continue that thermally direct circulation. And in addition, to say that there's some single T in, as if we have a real true hot reservoir, and a single T out is also not possible. These temperatures themselves are functions of the climate that they find themselves in. This is a system that is fully coupled, and there's very little external to it. And so we actually define Q in as just an integral over all of the places that are radiatively warming. That's what that plus means. Only the places that are being heated, not cooled. And if that's what our Q in is, we can then define a temperature, the corresponding temperature for all of those little, bits of matter in the Earth system, to define some weighted temperature that gives us our hot reservoir. And Q out and T out can be defined in similar ways. If we're to consider the Earth's circulation as a whole and not just this vertical gradient, we have to also note that we are much warmer at the tropics than we are toward the poles. And so there's a horizontal gradient as well, that the general circulation is constantly trying to destroy, constantly moving heat down gradient. And so Q in and Q out are functions not just of the vertical temperature structure of the atmosphere, but also the meridional temperature structure. And these are not externally set. So what is work in this system? It's a conversion between kinetic energy and potential or internal energy. And it has to be dissipated in steady state at the same rate at which it's produced. And there are two losses. And the loss that has gotten a lot of the historical attention in the literature, but for the last 25 years, has been the dry frictional dissipation. And this would be enough. This would be the primary or only loss of work if our atmosphere were dry, which is to say if it had no hydrometeors, if there were no drag and no phase changes. But it turns out that the frictional dissipation due to shear zones around things like raindrops and snow is really significant. And so the addition of water, and its ability to undergo phase changes is actually an enormous break on the ability of the atmosphere to do work on itself. The moister your atmosphere is, and the more capable it is of having hydrometeors and phase changes, in particular out of equilibrium, which is to say, for example, a relative humidity of less than 100%, subsaturation, the less energy you have to drive the motions of the ocean and the atmosphere. And so what people study in this field, including Paul and Frédéric Laliberté in this department, they've studied the ability of the atmosphere to do work in spite of the fact that there's an enormous drag on the atmosphere due to sedimentation and the cost of just lifting water up in the first place. The atmospheric heat engine can actually be thought of as two things, and this was clarified by Olivier Paul-Louis at NYU Courant. It's a heat engine, but it's also a steam engine. And so whenever the heat engine is directly moving hot fluid from down here where we live to 10 kilometers aloft so that it can cool, it's also dehydrating the atmosphere because that fluid is partially water vapor. And when you lift it up adiabatically, it cools, the water vapor condenses, and that's an irreversible loss of the system, of rain to your system. And so these are kind of playing tug of war. The atmosphere is dehydrating itself, which reduces its mechanical efficiency, while it's trying to move air thermally directly due to its temperature gradients. So we can define an actually more useful efficiency instead of the Carnot efficiency, and this is the mechanical efficiency. And this is actually the appropriate one to think about when we want to understand the efficiency of the climate system as something that can drive motion, large scale winds and currents. And so this is a ratio of the rate of working or the rate of producing kinetic energy available to drive these motions to the heating, which is, again, the same as the rate of cooling. Something really interesting about this system, which does no real work, but does tons of work on itself, is it actually could be more efficient than the Carnot efficiency. Because again, we're not exporting anything. This doesn't violate any laws. This should not be offensive. It turns out that this is the expression you get when you include the frictional loss of kinetic energy. And of course, the surface is down here where it's warm, and there's no surface aloft. Most of the friction is happening at warmer temperatures than the temperature at which energy is lost. So this factor right here is greater than 1, which means that the effective efficiency of our heat engine, the ability to do the maximum amount of work possible, if it were ideal, in a system where ideal also includes everything being dissipated to friction eventually, is more efficient than a Carnot engine. So this is just another image to help summarize the fact that most of the entropy sources in the atmosphere are not due to frictional dissipation of motions. They are due to water vapor and ice water and cloud water and rainwater. For example, we have large gradients, orders of magnitude larger gradients in the partial pressure of water vapor compared to the partial pressure of dry air. And so they're very significant non-advective fluxes down gradient from very, very moist regions to very dry regions. That's part of the significant source of entropy in the Earth system. There's also evaporation at subsaturation. Anything at subsaturation or supersaturation is obviously going to be irreversible. That's all a source of entropy. The fallout of precipitation is obviously dragging on the atmosphere. That serves as a sink of kinetic energy. And the frictional dissipation of the winds, which many early theories relied on to be the entire sink of kinetic energy in the atmosphere, is only 5 to 15%. So, so to illustrate the impact of having moisture in the atmosphere, for this review, we ran a couple experiments. One of an atmosphere in a box, a doubly periodic box. So what goes out, comes back in the other wall. It's actually an annulus topologically. And if you look at a level of 4 kilometers here at the field of vertical velocity in this perfectly dry atmosphere over a land surface with no moisture at all, it's very energetic. And you can see that the updrafts in blue have equal magnitude and abundance to the downdrafts. This is a very, very energetic, turbulent, dry atmosphere. As soon as you allow that bottom surface to be a water surface with, unlimited availability to be saturated, to evaporate into the subsaturated atmosphere, all of a sudden, the kinetic energy in your system collapses. This is the same scale. This is the vertical velocity, and we could see here that the updrafts have become very, very narrow. And these black lines indicate cloud patches. So our atmospheric activity just got much, much weaker, at least with respect to kinetic energy. And that's because we're now forming clouds, and those updrafts are much stronger and more localized. But most of the atmosphere is pretty quiescent and boring. And this is like the atmosphere we see outside. It's usually, blue skies or a big gray, but it's not very turbulent. It's not doing very much. All of the activity is isolated in these small storms because of latent heat release, because of the phase change once you allow moist parcels to lift adiabatically. This is a rendering of that plot on the right using software I haven't figured out yet. Marty did this. It's really beautiful. See this nice, almost kind of hexagon feature here of these lower clouds? Isn't that cool? This is cold pools colliding. When water vapor falls through the subsaturated lower atmosphere, those raindrops, they partially evaporate. And that makes the air around them really cold. And it sinks like a stone. And once that cold air mass sinks and hits the ocean, it moves out in every direction like a gravity wave. And those circular gravity waves collide, and they make these really beautiful packed patterns in the subcloud layer. So moisture radically changes convection in the atmosphere. When we ran just the dry case, the only type of energy flux we could get from the surface was sensible heating fluxes. So we're convecting warm air parcels aloft after they warm at the surface. As soon as moisture turned on, the sensible heat flux collapsed, but it was outdone compared to the dry case by latent heat fluxes. All of a sudden, we have enormous fluxes of water vapor from the surface, and that's necessary because these strong updrafts are, again, dehydrating the atmosphere. They are dumping out, they are wringing out the atmosphere aloft as rain. And so that has to be constantly replenished. And so we have this enormous latent heat flux. Moist convection can self-organize, and this has an impact on the efficiency of these circulations. On the left, we have this simulation, similar to the simulation you saw previously. This is in the early days of this simulation. You can just see it's not very well organized. We have clouds here and there. But if we waited 230 days, all of a sudden we got an aggregated clump of deep convection in the middle of the domain. And that's where it's raining. And it's very, very dry everywhere else. So which atmosphere do you think is more efficient? Which do you think has a higher mechanical efficiency? Folks maybe pointed that way. Can you try to point, okay, point that way or this way? Some pointing that way? Yes. Only Aaron got it right. It's this one. This is the more efficient. This has the higher mechanical efficiency. I want to remind you that mechanical efficiency relies on, it's a ratio, and it relies on things like the temperature difference between T in and T out, as well as the impact of the water vapor gradient. Turns out that the water vapor gradient in this domain is so enormous that there is a very, very large entropy source due to mixing between this moist region and the dry region. And so because of that gradient, there's a very high entropy source, and it serves as a brake on the mechanical efficiency. This is the more efficient engine. What you're probably perceiving accurately is the fact that this has higher precipitation efficiency. If you're a raindrop that wants to make it all the way to the surface and survive without being evaporated into oblivion, you'd much rather be here in the middle of this storm than in any of these. But this gradient really drives significant entropy production. Okay, I want to maybe, okay, I'll say a few things. So we've so far thought about enclosed atmospheres or the climate as a whole. These systems that are not exchanging any mass with their environment, but we can actually think about localized circulations, which absolutely do exchange all kinds of mass with their environment, as also being heat engines. And this is a classic example here on the left from my PhD advisor, actually, Carrie Emanuel, who's visited this department. And he showed that you can think about the overturning circulation of a hurricane or a TC, tropical cyclone, as a Carnot heat engine. But in reality, it's not closed. It's very open. And so unlike the climate system as a whole, or those simple experiments I was running just showing you a minute ago, there are significant lateral exchanges of water, momentum, entropy, energy with the environment. And so these systems are really interesting to study from a thermodynamic point of view. And in fact, we can model them in a space that many of you are very familiar with. This is an overturning stream function in height and radius space here of that hurricane. You can see that there is a lot of mass flux upward in the eye wall. There's outflow to large radii here beyond 800 kilometers. And then there's some subsidence, much slower subsidence in the farther regions. And here we have the eye wall over here. We can cast this in isentropic space. Just pretend this is, well, never mind this. We can cast this in TS space and see that we can indeed look at the overturning circulation of a hurricane as a heat engine. And the work that it's doing on itself and or the environment is captured by the area within these closed circulation lines. So you see here, excuse me, the temperature is the y coordinate and entropy is the x coordinate. So it's not a Carnot engine by any means. These 4 steps here you'll remember from an ideal Carnot engine, and that would yield a rectangle in TS space. Here we have more of a triangle. It's not that efficient, and most of the mass actually is not even carving out the bulk of the area in this triangle. They're messy. My student, Laurel, has studied the hurricane heat engine efficiency under climate change. And we found that even though the net heat energy and the total kinetic energy both go up as a function of sea surface temperature, that the mechanical efficiency goes down. And that's because as the atmosphere warms, the Clausius-Clapeyron relation tells us that water vapor increases by 7% per Kelvin. Now, that does not necessarily mean that that is a meaningful statement for something like a hurricane or the atmosphere as a whole, except we have found in observations as well as simulations that the relative humidity stays pretty constant across a wide range of climates, around the modern climate. And if that's so, then we are kind of effectively scaling as if we were in a saturated atmosphere. And so storms are going to get less efficient. That doesn't mean they're going to get weaker. They're definitely going to get stronger. So the part that matters to us economically and socially in terms of staying alive is we have nothing good to say. But the mechanical efficiency has to go down because the amount of water vapor in the atmosphere is going up so rapidly. And so that comes at a cost. That's just another brake on the ability of the atmospheric heat engine, or here the hurricane, to do work. And that's because the two sources of energy that are required to drive a hurricane, the water lifting energy, the ability to move water back up in the atmosphere because in a response to dehydration, as well as the Gibbs penalty due to phase changes out of equilibrium, go up so rapidly. Now let's consider briefly other planets. I did my thesis work and my first postdoc work on Jupiter and Saturn. So I have a soft spot for other planets, although I've very much picked my favorite and decided to stay here. So they're really different than Earth. And it, climate scientists have some danger of getting stuck in a way of thinking that, constrains physics to just what we observe or just what we can imagine on Earth. And that's a really, really limited framework. And so it's important for us to push our boundaries and to think about really exotic systems elsewhere. For example, Saturn and Jupiter and Neptune are probably still stratifying. That means that, like a salad dressing bottle that you've just shaken, they are sorting their constituents within their deep interior as a function of density. And so right now there's helium rain raining through hydrogen envelopes in these deep planets because helium is pretty heavy compared to hydrogen. So that's happening a lot. So these planets are actually, first of all, we know they're not in energy balance because they radiate like twice as much energy as they get from the sun. And so they're still cooling down. They're cooling and they're contracting. And that loss of gravitational potential energy in the cores of these planets is being radiated as long wave energy. And so these planets emit more than they absorb from the sun. So they're definitely not in energy balance. They shouldn't be in entropy balance either because they're ordering. The net entropy of these planets is probably going down. And then an interesting question is, well, when we look at the weather fluid envelopes of these planets, when we see these storms and jet features and small scale features, are those in some kind of steady state? And the ordering is happening at a much deeper level? So this is a really interesting question that obviously we can't go observationally tackle, but we have numerical models that let us ask questions like this. I've talked a lot about the impact of phase changes on the climate system and the impact it has on your ability to do work. Mars has periodic global scale dust storms. So it's not really raining there, although there is sometimes CO2 snow on the poles. But on Mars, the primary source of dissipation that isn't just frictional dissipation at very small scales in a dry fluid is actually drag due to dust. And it's super aperiodic. And so that's a really interesting puzzle to think about. Also, the primary entropy sources that happen on Earth are due to the vertical temperature gradient. They happen in a column. Vertical temperature gradients and moisture gradients are where the bulk of entropy production comes from. That's not true on places like Mars or Titan or tidally locked hot Jupiters. for all of these planets, it's the meridional or longitudinal temperature gradients that are responsible for, their effective heat engines driving the motions of the planets. Venus is another really interesting case. Venus used to probably have a very active hydrological cycle before it lost all of its water. So it is an outlier among the planets in the solar system for mechanical efficiency. We think its efficiency is very, very close to the Carnot efficiency, whereas Titan, which has an active methane cycle of rain and clouds, and Mars with its dust storms, and then these giant planets with all their exotic rain and dynamics, these are very, very far from ideal heat engines, even in the climate context where Q in equals Q out. So in a departure from what I've talked about previously, there's another way to think about these systems thermodynamically, and it has nothing to do with heat engines. With a heat engine, you have some system, and you have a hot reservoir and a cold reservoir. And I talked about all of the tricks we have to play to get there to be a hot reservoir and a cold reservoir, because they're actually really components of the system itself. They're very much part of the solution. But there are systems on Earth. In the top row, you can see these eddies around Southern Africa, the polar vortex here, small sub-mesoscale eddies deep in the eye of hurricanes, and then, of course, the famous Great Red Spot as one of the examples of vortices abroad. These systems are not meaningfully connected to two different reservoirs. It is not meaningful or relevant to consider a hot reservoir and a cold reservoir when considering these pancake-like vortices, these very flat, very large-scale vortices that are set up in nearly inviscid fluids that are dominated by the characteristics of stratification and rotation. These are acting a lot like 2D inviscid flows, and there's a whole field of study devoted to this, and one of its names is called Hamiltonian geophysical fluid dynamics, where we can consider these as conservative systems, not attached to hot and cold baths, but rather as systems that are isolated and approaching steady state. Now, of course, all fluids in nature are not inviscid. There's viscosity everywhere, but people working in statistical GFD do a really cool thing. They say, over the timescales we're interested in, well, over the lifetime of one of these features, like this polar vortex or these eddies in the ocean, we can consider the total energy of these features to be conserved, but something is being lost. And that is entropy. Entropy is just a vorticity squared. It's just a quantity that kind of measures the filamentation of fluid flows. And because entropy cascades downscale to tiny, tiny scales, and because there is a little bit of viscosity, we actually lose entropy, while a more rugged quantity, energy, is cascading upscale. And so there's this long time period where we can say, you know what, we're losing entropy because it's not inviscid, but energy is really not moving much because it's a very, very large scale quantity. And that allows you to use variational principles. And it allows you to, for example, minimize entropy while keeping total energy constant. And when you do that for systems like this, you can actually back out qualitatively similar vortices, that these are meant to live a very, very long time under these constraints of stratification, rotation, and low viscosity. And in fact, for the Great Red Spot, some really nice work, I think maybe it started in the 90s. Where is my mouse? There we go. Has shown that you can actually conserve infinite quantities, which is appropriate for fluids in the thermodynamic limit, and actually back out something like the Great Red Spot. And so it's possible to do a very different type of statistical mechanics for fluid flows in particular, and discard the idea of reservoirs, hot and cold reservoirs, and still use entropy, but now Boltzmann entropy, to think about how these can last for a very long time. So that's pretty exciting. An example close to my heart is the fact that it's possible we've seen the first example ever of vortex crystals in nature. So this is pretty remarkable. Back in the 90s, this paper is from fine 1995. A 2D electron plasma was shown to be able to have steady states of packed polygonal vortices. And these states were called vortex crystals. There's no rotation here. And in these systems, these are just steady states after you allow this pretty and viscid fluid to mix. And that's interesting. It doesn't look like it should be in steady state. That looks like something that should be out of equilibrium. But those would just last a really long time. And then Juno got to Jupiter and had a look at the poles directly for the first time. And we found this. These are all cyclones. This is what? 1, 2, 3, 4. 8 cyclones around a central cyclone on the North Pole. And this is 5 cyclones around a central cyclone at the South Pole. And every time Juno has made another loop around Jupiter, these barely change. And in fact, they're rotating in solid body rotation with the planet itself, or close to solid body rotation. This seems really, really, really stable. And so of course, we know that Jupiter is pretty inviscid, just like Earth's atmosphere is pretty inviscid, but there's some viscosity. And so it's remarkable that a planet like Jupiter, which again is radiating more energy to space than it receives from the sun, which means that the atmosphere that we perceive on Jupiter is being heated at depth. And that heat has to be translated through convective motions to radiate out at the surface, at the level where the opacity plummets. And so Jupiter is an extremely forced and dissipative system compared to a true and viscid fluid. And yet we can have something that appears a lot like vortex crystals. So this is an area of active research, including one of the undergraduates in my lab. The last thing I want to tell you about is this thing that won't go away called the Maximum Entropy Production Principle. And so some of you are familiar from statistical mechanics with the maximum entropy principle, where, like the work I mentioned before for geophysical flows, you can constrain a system to keep constant energy, and then you can maximize the entropy for systems in equilibrium, and you can solve for the equilibrium flow or behavior. That's good physics. That totally works. The Earth is extremely out of equilibrium, right? It's even hard to design a thought experiment of what the Earth would look like in thermodynamic equilibrium with its environment, because the only valid reference temperature would be the several Kelvin deep chill of space, and that would still only be valid if you turn the sun off. It's really hard to imagine Earth in any kind of equilibrium at all with its environment. You can make some guesses, though, if you want to go halfway, if you want to turn the sun off and not let the Earth radiate anymore, maybe put insulation around it. The constituents would shake out just like a salad dressing bottle, and it would become perfectly saturated. There would be no hydrometeors, so no clouds, no motion, obviously. But this is not really a well-posed problem. It would be very nice for us to discover a principle, some kind of minimum or maximum principle that we could apply to the climate system so that we don't have to solve the dynamics, because the dynamics are really hard to figure out. They involve solving the Navier-Stokes equations. It's really expensive to do that. That's why we have supercomputers dedicated to climate projections. So Paltridge in the 70s decided there should be a minimum principle of some kind. Let's try it. He ran a really simple model, 10 boxes from pole to pole. He had a few parameters, and he let one free parameter be solved by maximizing the entropy production. So he just minimized entropy transport between the boxes, and he got a reasonable result. And his conclusion was the climate system must therefore adjust itself to be in a state that maximizes entropy production. So that is a principle, and that is not held up well. So it fails when applied to vertical transport. And as I mentioned before, that's where virtually all of the entropy is created in the Earth system. So this is the fine model. If you have, a box for the atmosphere in the tropics and you compare it to a box for the atmosphere at the poles, it works, I guess. Subjectively, that result wasn't compared to anything. It can't account for previous climate states or future warming. In fact, when the MEP principle is applied to things like global warming or deep climate states where we know certain variables change in a big way, it does not reflect the huge climate swings that we've seen in temperature and ice cover. Specification of the optimization problem is ambiguous. So for example, this principle does not know the rotation of the planet. It doesn't know the obliquity of the planet. It doesn't know the ice cover. There's just a lot of other stuff you have to add. And as you keep adding constraints to your climate problem, you no longer need a variational principle to close it. You've just solved the problem. You know what climate you're going to get. And then finally, it lacks a sound physical basis. Now, this was bravely attempted in the 2000s by someone who used Shannon entropy from information theory to try to show that there could be a maximum entropy production principle. But then authors a few years later said, look, all of your derivations are only valid in the limit very, very close to actual thermodynamic equilibrium, which the Earth, again, is nowhere close to. And so, I would have thought that closed the book on MEP. But now people are trying to recast it as a maximization of power instead, or a maximization of working, responsible for economics and all biological life on planet Earth, governing river dynamics, and the Gaia hypothesis, or the Gaia hypothesis, I don't know how to say it. People in this field have said that we could think of it instead as an inference algorithm, which makes it not falsifiable, which should give you a lot of confidence in the usefulness of this principle. Literally, they said, well, if it's an inference algorithm, then when it works, that's a system governed by MEPP. And when it doesn't work, that's a system that is not governed by MEPP. So anyways, this is how we closed our review and reviews of modern physics. So you're welcome to check out the spicier parts. But that's all I have to say. So that is a wild ride through thermodynamics of the climate system. I hope that you learned a little bit about Earth, but as importantly, you learned about other dramatic systems so that you're not too stuck in the fact that, you know, water vapor is our condensable constituent here. You know, on tidally locked exoplanets and hot Jupiters, it's titanium dioxide, right? That's what's changing phases and making clouds on other planets. So there's just a lot of fun to be had thinking about these kinds of problems. And then the most important thing is, what can we learn from it? And we can learn about the efficiency of the climate heat engine and its ability to do work and drive circulations, especially in a warming climate in the future. So that's why these tools are interesting and valuable. So I'll take questions. Thank you very much.